All right, there's a junction in this circuit. It's a parallel circuit, and to be parallel means the objects are going to be experiencing the same potential difference. So if you have objects that are in parallel, they're going to have the same potential difference. And you can see that here too, right? That the potential difference is here. This set of capacitors in parallel all are connected across the same potential difference, meaning the potential difference from here to here, from A to B, is the same potential difference as from C to D. They have to be at the same potential because they're joined together. So any differences in potential would level off. I want to be a little forthright with you. Parallel can be drawn a lot of different ways. So this circuit, which is a little messy, but I'll clean it up. But this circuit is also a parallel circuit and would be the same. It would be considered the same orientation, the same, parameters and properties as the circuit on the left. In fact, it wouldn't be too big a stretch to have two objects in series inside a parallel like that. But still, the potential from A to B and the potential from C to D would be the same. That's what defines a parallel circuit. And although I'm doing two parallel, and I call the individual parts here, I call them legs of a parallel portion of a circuit, you can have all sorts of things in parallel. You don't have to be stuck with just two things, okay? Everybody following along all right? All right, so let's get to analyzing the circuit using Kirchhoff's laws. Now, I'll remind you that with Kirchhoff's laws, each loop has to have a potential that sums to zero. I see three possible loops through this circuit. Do you guys see that? Yeah, I see one like this. That's a possible loop through the circuit. This is a possible loop through the circuit. And this is a possible loop through the circuit. Kirchhoff's laws generate an equation for every loop through a circuit. So if we just number this 1, 2, and 3, we'll generate all of our potential equations that we can use for this circuit. Now, there's a lot of redundancy here. The truth is you only have to generate enough loops to cover each circuit element. So I wouldn't have to do all three. I could just do two. Any two of these would cover every circuit element in the circuit. Do you guys agree with that? So I'm going to write out all three so you kind of see it done, but ultimately we would only need two of them. And I want to remember I should check the polarity of the objects first, because when I deal with potential difference, going across an object and you're going from negative to positive is a positive potential difference, and going from positive to negative is a negative potential difference. Is it clear from the way this is arranged that if this is the negative and this is the positive, that would have to be the same orientation on those two capacitors? All good? Any questions about that? Yeah.
So I understand how the capacitor from the positive and negative are pulling electrons. So why doesn't that just make the battery neutral if it's like pulling?
Because the battery has some kind of the word we use, which is inappropriately like it's an inappropriate word because it's not really what's happening, but it's stuck. There's an electromotive force inside the battery that is actively separating charges. So whether we're using a power supply that has some kind of transistor amplifier element in it, or whether you're using a battery which is having an acid redox reaction, there's an active system so that when when an electron enters the battery, it is actively moved from the cathode to the anode. Does that make sense? Until the acid runs out. That's not true on the capacitor, which is not a active device like that. Is that okay? All right, so it looks to me like I'll have in my first loop, I'll have the EMF is positive and the voltage across the first capacitor is negative, and that has to sum to be equal to 0. In my second loop, which is the big one around the outside, my EMF across the battery is positive and my voltage across the second capacitor is negative, and I'll set that equal to 0. And in my third loop, which is, it's redundant, but I'm going to put it in here anyways. My third loop, the voltage across the first capacitor will be positive, and the voltage across the second capacitor will be negative, and that'll sum to be 0. Now, if you look at these three things, ultimately you realize something that I already said at the very beginning, and that is every portion of a parallel circuit is at the same potential. Can you see that that's what that's telling you? I mean, just do a quick little solution here, and you realize that these are all equal, and therefore they're equal to each other. No big deal? Everybody see that okay? All right. It doesn't tell us very much, but it gets us started. I'm going to get these loops out of the way now because they've served their purpose. The next thing I want to talk about is the junction. I'll remind you that charge in has to equal charge out at a junction. Now, there's no moving charges once the capacitors are fully charged because it's an open circuit, but there was a time when the charges were moving. And charge had to come out of the battery and split here with some charge going this way and some charge going that way. You guys follow what I'm saying? Because, I mean, if you have 3 electrons approaching that junction, you have to account for all 3 electrons. And some of the electrons are going to travel along one of those paths, and some of those electrons are going to travel along the other. So in this circuit, the total charge that left the battery will have to equal the charge that settles on capacitor 1 plus the charge that settles on capacitor 2. Charge in equals charge out. So again, this is conservation of energy as it applies to circuits, Kirchhoff's first law. This is conservation of charge as it applies to circuits, Kirchhoff's second law. Last, we know that we are trying to find an equivalent circuit. The battery doesn't know that there's 2 capacitors or 50 capacitors. It supplies charge based on what it sees as an equivalent capacitance. So this value, this total charge that the battery pushed through to the circuit comes from remembering that capacitance is charge divided by potential. So this total charge, Q, it had to be the capacitance equivalent times the EMF. Knowing that Q1 is what settles on capacitor 1 and Q2 is what settles on capacitor 2, we can make a similar relationship. I think we can probably all agree that V1 is going to have to be Q1 over C1. And V2 is going to have to be Q2 over C2. Everybody okay so far? You see where I came up with that? So Q1 equals V1 C1, and Q2 equals V2 C2. See, that was a fine sneeze. It sounded like a regular one. It was a solid hachu. Where are we going to rate that? 7? Are we going? So you want a 10-point sneeze rating? Like there's 10 different variations in sneezes that requires that kind of. I mean, I always think just a 1, 2, or a 3. What's that? You think 5? A happy medium is 5? All right. So based on Nick's assumption, I think that's a solid 3 or a 4. You think it's above average? All right. Well, 3 would be average on a 5-point scale, right? All right. 4 out of 5. 4 stars? All right. 4 stars would repeat. I'm good. All right. I'm really glad I'm recording this today. All right, so I want to bring all these things together because eventually I want to get to a conclusion here. I'm going to substitute into this function because this would bring all of the capacitances together. So what I do, I'm just going to move this to the side a little bit so we can kind of see it. I'm going to get the equivalent capacitance times the EMF has to equal C1 times V1 plus C2 times V2. But we also know that the potentials are the same across all of them. So I think I can just divide out by the potential difference, leaving me that the equivalent capacitance is equal to the sum of the capacitors that are in parallel. Pretty straightforward. Now, this was using Kirchhoff's laws like this to show how a battery views a parallel capacitance system is just really me trying to give you evidence of where the things I'm about to talk about have come from. We have series circuits, or a set of capacitors in series. The equivalent capacitance is based on summing the inverses. When we have parallel circuits, the equivalent capacitance is based on the absolute sum of the total capacitance. This is on your equation sheet somewhere, and it's probably written like this. Something like that, some summation set. Not particularly tough, but you get the idea a little bit? Because here's what I'm going to expect you to do. Let's consider this circuit. All right? And let's say that this is a 3 farad, and I'm using simple numbers kind of on purpose so that it'll be easy for us to deal with. Let's do let's say it's a 6-volt battery. Now, no circuit would have this kind of sized capacitors. When we do this in practice, or you do this for like a test, they'll probably be in microfarads or nanofarads or something like that. Just leaving it, I mean, the unit won't matter. They will give you all of them probably in the same order of magnitude. So don't worry too much about that, but I'm just wanting to use some simple numbers. I want to solve this circuit, which means I want to find out what the equivalent capacitance of this circuit is, and then I want to work backwards to figure out how that 6-volt potential difference gets divided up amongst all these elements. All right? We're going to do something called stepwise reduction. And you have some guiding rules that we already talked about. And those guiding rules are this: capacitors in series all have the same charge, and capacitors in parallel all have the same potential difference. You need to remember that. It's a rule that we're going to be using quite a bit throughout the rest of the year. Capacitors in series all have the same charge. Capacitors in parallel all have the same potential difference. The process of stepwise reduction is the process of taking a complex circuit and making it more and more simpler through a series of steps. And we have to work from the smallest, most inside element outward. For example, I have two capacitors that are in series and two capacitors that are in parallel. But I have series in series with a parallel element. Do you guys kind of see that? So the first thing I could probably do is I could take this circuit and reduce it down by maybe picking either the parallel or the series to make simpler. So let's maybe make the parallel element simpler. So I'm going to redraw a circuit, and the shrewd among you realize you can probably do multiple steps at once. I'm not going to today. I'm going to just take that parallel element and reduce it, and then I'll come back to those two that are in series. Now to reduce that parallel element, I recognize I have two capacitors that are in parallel. And as we just showed, the equivalent capacitance for those would just be the sum of the two capacitors. So the total capacitance for just the parallel portion will be 6 farads. All good? Great, no worries. I now have 3 capacitors that are in series. So I want to reduce that down to a single equivalent capacitance. Again, I have a rule for this, but this rule requires that I deal with the inverses. So it might take a little more work. I'll say that the equivalent capacitance will be 1/6 plus 1/6 plus 1/3. If I get common denominators, I believe I'll get 4/6 or 2/3, and that's my inverse of the equivalent capacitance. A bunch of you will forget at the end of this to invert your answer, but please make sure you don't forget that. The actual equivalent capacitance is 3/2 of a farad. All good? Not particularly tough? This stuff is much easier than what we've been doing before this. The math is simple, the rules are simple, but they're probably different than what you've done in the past too. So that means the equivalent capacitance is 3/2 of a farad. There's no problem using decimals. I'm not scared of fractions, so I tend to use fractions when I can. Now, that's the reduction part. To actually solve the circuit, we're going to work backwards now and try and figure out what the voltages are and charges are on all the capacitors. Right now, I know that although it's 3/2 of a farad, the battery, 6 volts, thinks it's connected up to a single capacitance that's 3/2 of a farad. So I can figure out how much charge the battery pumps out to the circuit, right? And that's just going to be the capacitance times the potential difference, Q equals CV. We're just going to use this over and over again. So in this case, 6 times 3/2, 9. So 9 coulombs of charge. All right. Now, here is where things get a little dicey. We're going to go back a step. I like drawing all these arrows. Let me know what I'm doing. And we're going back to a system that is in series. So we need a rule here to figure out whether we take the voltage back or we take the charge back with us. So remember, there's 2 rules. The charge on capacitors that are in series is the same, and the voltage is the same for capacitors that are in parallel. Well, I'm going back to a series, so I grab the series rule and I apply it to the capacitors that are in series. Every capacitor in series there must have 9 coulombs of charge because the equivalent capacitance had 9 coulombs of charge. But that's not really the capacitance that was there. It was 3 capacitors in series. So in going back to series, we apply the charge. So 9 coulombs, 9 coulombs, 9 coulombs. All good? Pretty easy. Now, when you go back a step, you need to stop here and figure out the thing that you are missing. There's only 3 things: capacitance, voltage, and charge. So for each of these, you should have 2, and we do. We have the charge and we have the capacitance, so we can figure out the voltage across all 3 of these. So take this, voltage is equal to charge divided by capacitance. So I'm going to have, for the top one, 9 divided by 6, or 3/2 of a volt. 9 divided by 3, 3 volts. You all right over there? 9 divided by 6, 3/2 of a volt. All good? Now, check your work. There had to be a total of 6 volts of potential difference. So if you add those up, do you get 6 volts? Yeah, 3/2 plus 3/2 plus 3 is 6. Every step you have a chance to check your work. So in the early parts of this, if they don't add up to be what you expected, you've made a mistake. It's probably arithmetic, it's probably small. But now, these were the original capacitors in the circuit. So I don't have to do any more work there. This one's 3/2 volts and 9 coulombs. This one is 3 volts and 9 coulombs. But I am going to have to go back and split up that capacitor. Let's put this along the top. So for parallel, we apply the voltage. Parallel elements all have the same voltage. So since this 6 farad capacitor is actually 2 3 farad capacitors that are in parallel, they must have the same voltage. So I'm going to grab that 3/2 volts, and I'm going to apply it to both capacitors that are in parallel. So 3/2 volts here and 3/2 volts there. Now again, I can figure out the total charge, or the charge across those 2 capacitors, by using Q equals CV. So looks to me like I have 9/2 coulombs here and 9/2 coulombs there. You can check my work. The total amount of charge I was supposed to have in the capacitor is supposed to be 9 coulombs. 9/2 plus 9/2 equals 9 coulombs. Now, that's more or less solved. The last thing you're supposed to be able to do is figure out the energy stored in any one of the capacitors, 1/2 CV squared. That's just a formula. Plugging that in is no big deal. It doesn't play a role in the solution, in solving for it. But this is how you would figure out how much individual energy is in each one of the capacitors. Stepwise reduction is not terrible. It's definitely easier than using Kirchhoff's laws. In this circuit, we generate 3 equations using Kirchhoff's laws because there's 2 major loops in the circuit, and we'd have a third one that'd have to do with the junction. It would not be easy to do. But stepwise reduction, although cumbersome, has some steps, it's just simple algebra. I mean, it's not even algebra hardly, it's mostly just arithmetic. So I want you to practice one. You guys good to try one out on your own? Let's try one out. You guys try it.
No, he doesn't get it, but he gets it.
Somehow he gets it. You're the greatest test taker of all time.
Do you understand?
So I lost it.
All right. So you're kind of like making a map of how you want to solve your circuit, starting with the most inside elements first. How we doing? So did everybody get 2 farads here? All the way at the end. So the 6 and 3, we did that first, right? You got 2 farads here, and 4 farads here, and 3 farads here. Well, this one's the 3 farad, but I have the 2 and the 4 in parallel, so I just add them together and get 6. Well, this is just the same 1 over 3 plus 1 over 6 we've seen a couple times. Add those together, invert it, and get 2. Pretty easy? All right, 6 volts, 2 farads, 12 coulombs. 2 times 6 is 12. The rest of this is Q equals C times V. When I go from my capacitor by itself backwards to a capacitor set that's in series, what do I take with me? Charge, 12 coulombs, 12 coulombs. If I want to find the voltage, that's right. So I take my charge divided by my capacitance and get 4 volts, 2 volts. Do those add up to be 6? All right.